Swayam Prabha. Digital India. Educated India.
So I mentioned so many. The area we are looking into, that's Australia. Again, this is a Logan catchment we are looking into. That's a lower Logan catchment. And also there is a dam upstream. Actually, we're having some debate on this one. And this dam, there is a water sports competition in 2032 Olympic Games. Some want to have the water sports over there, but Gold Coast want to have some water sports on the Gold Coast. So we still have some debating on it. Yeah. So here is the dam. So we will see how we are able to, actually our study will help them to do some evaluation. So what is the water quality and conditions, and what is our, how we manage this dam. So that's what we are having over there. And this Logan catchment, the purple one is the Logan River, and the yellow one is the Albert River. So they formed over here, they meet, and then coming all the way to this is a Mountain Bay. The lower part of Mountain Bay. Okay, so here is some information we have for this area again. So we also have measurement point in Logan River, and this one is in the Albert River. So we have the discharge measurement, the rainfall discharge measurement over there. And then we look at for how many years. This is from 2003 to 2018. And again, what do we look? We look at all those discharge, rainfall, temperature, salinity, and TN, TP, and turbidity. So those are the key parameters we are interested in. So then we do some statistical analysis, try to see what's the variation for this is the different months, the seasonal variation. So that's from, let me see, from November to October. So that's what we are having. So we will be able to see, okay, for you can see the medium water temperature that's peak in summer. That's our January. So that's around here. So very clear. So that's a distribution, right? And then you can see salinity levels. So most of the remains low throughout most of the years, except for this discernible peak that's in the concentration at the end of a dry season and the start of the wet season. That's October. So that's for salinity, you are able to see. And also for the Albert River, for the TN and the TP. So most of the time, they are quite consistent. They are quite consistent, quite consistent. So that's for all of that. So that's a seasonal variation. We try to understand the system. And then we look at this one. What's this one? What's this diagram? So this diagram, again, one is the Logan River, one is the Albert River. And this is a drainage you are having. So this side is a river mouth, and then on the inside is the upstream. And the same thing over here. So this is river mouth, near the river mouth part. So we'll be using this diagram to show. So that will be coming from here all the way. So that will be, you can see, that's along this one. So you will be seeing over this, okay? This will be river mouth. And in this area, we have a dashed line. There is a wastewater treatment plant located. So that's where the discharge will come in. And over here, there is another wastewater treatment plant. So you can see there is a peak, right, for the water quality parameters. That's because of the discharge from the treatment plant. It will affect downstreams. So our monitoring result actually captured this very clearly. Same thing over here. So that's what we are having. Now we also would like to see the impact of the dam. So this dam is impounded in 2010. And also this box diagram actually is a distribution of TN and PP and the turbidity. So 3 different parameters. One is a pre and also post the impound period. So left-hand side, that's pre, and the right-hand side as a pro. So what's the difference you are able to see? Actually, after the completion of this, the water quality has been improved because the dam completed. So the dam has played a big buffer zones in the upstream. So that's what we are able to get from the result. Very clearly showed that. So that's an impact of the dam which has been played on the water. But then we will see, okay, what are the future issues we are able to investigate. So, of course, we mentioned about the urbanization or the significantly, and also the increased influence because of the more populations and also the usage of water, and also during the drought and urbanization, what's the nutrient level. So all of that is what we need to pay attention to. So we mentioned in the previous slides, we need to use a numerical model to do the analysis. So over here, we are going to see what we have been doing. Yeah, again, here, apart from those models, we use a global scaled. We start from the global scaled climate change model, then of course to the downscaled regional study. This actually has been done by the Queensland government. They have downscaled the model to 10-kilometer resolution. But in Australia, in Victoria and New South Wales, some region we have been downscaled to about 4-kilometer resolution. So that's in some other regions. But what we are doing over here, because we are in Queensland, is a 10-kilometer. But we are working on the even finer. So of course, anyone will have those like a bias correction for the climate model. Then is our hydrological model. So we are using the SWOT, NAM, and SWOT. So apart from that, we also did the site scale flood analysis. So then coming back, we're looking at all of this one. So we have the temperature. Actually, we look at the temperature and the precipitation. That's again from there, also downscaled to this one. So we all use this for the local climate change model, then our LAM and model. Then we come to our 1D and 2D incoupled microflooding model. That's the whole areas we are doing over here. And then is the water quality. So that's the whole thing. We integrated together. But that's for modeling part. Of course, we have all those measurements as well. And when we are doing the climate scenario, we use a daily high-resolution climate projection from coupled IPCC models. We use the 11 models. We run the result for each of that. So downscaled 10 kilometer. Also is a daily, and that's from 1980 to end of is 2099. So that's what the climate change model we use. And we run the high emission, the RCP 8.5. Actually, we also run the lower catchment, low emission. And then is a sea level rise. Also, again, we use RCP 8.5. And we defined 3 different time periods. So that's just for so you are able to see that's every 30 years, 30 years, 30 years is 3 different periods we are looking into. So that's how we define that. That's are the models we have been selected to use. So each model, the result is there are some different, but we include all of that in our study. So we did some calibration of the model. And so this result here is from the LAM. And we have different sites we selected, and we did some comparison. You are able to see how we get the different performance. And we are having both. One is a calibration period, that's up to here. And then we have our validation period is doing this. The last nearly 4 years, but previous 10 years we use a calibration period. So that's a model we try to. That's for hydrological model part. And also we also benchmark the inundation area. So this is for the catchment. So you know that the river is over here. So the river. So we also have this one coming here. And this is one of the events. Let me see. That is. Let me think. That's okay. This is a baseline event. So that's a baseline event. So we use this one as a baseline event. What's the white lines over here? So the white lines over there. That's from the satellite image for the flooding. So the blue colors, that's from our model result. So we compare that blue shade and the white lines. So they are in a reasonable good agreement, actually very well, except this area. So the reason is we try to understand why we didn't get a good understanding on that area. So this is a sugarcane, is an agriculture area. And also we didn't have a lot of good information when we defined that area. So for now, another group, they started monitoring in that area to try to get a lot of information over there. They just started. And before, a lot less attention was put over there because it's agriculture. So the risk is less compared to the urban area. But now we are looking into that area as well. One thing is how we develop that in the future. But at the same time, we also try to have a good understanding what is missing when we are doing all of this study. So very recently, a project has been started over there. But that's for monitoring. So once we got a good monitoring, we will try to use those results to our model. So this is a baseline. So you can see they are in a very good or reasonable good agreement from monitoring and the modeling. So now then we are able to see, okay, how we are going to apply the climate change in this study. And remember, before I mentioned, we defined 3 different periods. So those 3 colors are those 3 periods. And from our analysis, you are able to see that's a precipitation. You can see what's a rainfall change in the future. Actually, they are not the same, or they are not linear variation. So they varied in different months, are very different. And this is for the months, and this is for the 3 different periods. So you can see for this one, the variation there maybe is increased all the time. But for some season, it's going down. So not the same for all the seasons. So varies with the season. In the summer, in the winter, they are all very different. And this is evaporation over here. Then you are able to see. Basically, they keep increasing for all of that. But the scale of the change is not the same. It's very significant. So that's try to understand those climate index. Then we will also looking into the monthly mean flow. This result actually is from swatch. We also set up a swatch model, and then to see what is future climate change of the flow conditions. So based on those input from last slide, the rainfall and the evaporation, then we will see what the river discharge rate changes in the future. And also you are able to see the mean monthly river flow decreasing very significantly. That is a mean, okay? This is a mean. So that's in Queensland. And of course, for different seasons, they have different changes expected. So that's what we are able to see. That's a mean flow. It's a mean flow. Then we look at the flood. Again, this is a color. This is a color for 3 different periods. And this one for 5-year event. So 5-year event, the change is not that significant. But when we are coming to the more extreme event, so that's a 50-year event, you can see in 2020, that 30 years period, the distribution is like this. But when we are coming to, But when we are coming to later stage, so you will have more like extreme event concentrated. Before that is more like the expanded. So they are looking different for the prediction in the future. So then we use a cyclone Debye, that's a real data set, and then to predict in the future what it look like. So that's a river discharge. The blue lines, that's a baseline. That's a real one. And the purple one, that's 2080. That's 2080. And we have the 2020 and the 2050 prediction. They actually close to each other. They are all like close to each other. But in 2080, you can see actually is not keep changing. Actually, is lower than the previous two periods. So that's we are looking into what's different for the previous one. So what you are able to see, if we are using this data, you can see this is like a median. It's lower than the other two, right? This is a box diagram. So this is a 2080. This is a 2080. So the other two, they are close to each other. They are close to each other. So similar things, if you are looking at a 50 years event, also the 2080 prediction is lower than the other two periods. So it's not keep increasing for this flood event. So what tells us you need to keep looking into the climate change model outcome. So then to adjust our future planning. So we cannot say, okay, now we did that, is this trend, then just project that keep rising. So we have to look at constantly to get our analysis. Then we continue this study. So we have our future study. So the future study, what we are having, one thing, we have both RCP 8.5 and 4.5, two different scenarios. And we also have our 3 different periods. So you have a different sea level rise included. Then we do the prediction for the inundation area. So the red shade, those contours in the red, that tells you the increased inundation. The increased inundation. So we are able to see from here for the different years. So this is a baseline comparison over there. And then this is another 2050, 2080. So that's you are clearly to identify where you have a new. This is a new increased inundation area. And this one you have the climate change and the sea level rise included in. Oh, sorry, that's a storm surge. This is a storm surge. And what is most? This is the sea level rise and the storm surge. So here you have quite a big increased area. But I would say because our previous study, that area, the big red area, actually there's a big question mark. I would like to revisit and study that area. Yeah, because that model in that area, there are a lot of the uncertainties. So with this model, you are able to do a lot of things. Of course, you can change the land use, and then that will be starting from your hydrological model to get your output. Again, that will be coming to your hydrodynamics model as well. Yeah, so apart from those spatial result, we also look at the saline intrusion models along this area, the Logan River and also the Albert River. So the blue lines, the blue lines are the simulated, and the circles are the monitoring. So we have a kind of a good agreement between the saline intrusion model. So it's we are quite happy with that. Again, we also did the calibration. That's for the SWOT model. We use a SWOT cap tool for the calibration. So that's some AI techniques has been embedded. So it's already embedded by that. But then we did this one for the comparison. The right-hand side is for the stream flow comparison. But the right-hand side is for the TN, the total nitrogen comparison. So it always, for us, so the legend is too small. So always for the water quality is our big concern when we are coming to the water quality modeling. So a lot of the discrepancies over there as well. So that's a lot of things can be done. And we are also looking into whether use the AI model, try to improve it. Yeah. So, but we have to use physics-informed AI. We cannot just purely based on the data. Like some study, they just purely based. But for the scientific problem, we always try to use the equation together. Because when we are using the equation, we are able to control the loss function in the AI model. Then, which means give it some a restraint. So you cannot go wild purely based on the model. We still have this physics law to control it. Yeah, so that's what we are, it's still going on. We are trying to do in that. This is also the comparison between our model result and also the monitoring result. You are able to see. So they are in a kind of agreement, but still a lot of things can be done for those data sets. Yeah. So we are also trying to do some clustering of all those results. So when the flow is low and the flow is high, we try to separate that into a different cluster. Then to do the monitoring. So that's, again, is a AI-based or data-driven model. But we still, based on the existing modeling results or modeling tools, we also did the similar things for the water quality prediction in the future under the different climate change scenario. But for this one, we just use that as a trend to see what the trend will be under this circumstance. So again, that's still 3 different periods, but this is a seasonal. So also you are able to see that the difference for each month is very significantly different, the distribution. For example, if you're choosing, this is a March, and this is a September. So there are variation in the future for those 3 periods are very different. So they are very different. So then, of course, you have to look back all of that. What's the cost of those difference, and what is the future concerns we need to pay attention to. So what I want to say is you are able to use this as a very good tool, the numerical tool, to do a lot of the studies. So in the last few days lecture, we didn't cover the hydrodynamics or water quality, but all the things is quite similar. The logic or the method framework is very similar to what we are using. So for waves, we try to get a good understanding of the waves or model the waves. Then we are able to use that for the purpose of your study. Here, for the hydrodynamics, it's the same. You also try to get a good outcome from the hydrodynamics, how that drive the water quality, drive your further analysis of the climate change. So that's what we are having over here. So that's just a quick summary about what we have been talking about here. And so we have 10 minutes to have our free discussion or chat or whatever. Yeah, thanks very much, and really pleasant to have this opportunity to share some of my work and experience with everyone. Thank you. Yeah. So any questions? Sorry, how?
Tidal range is less than 1. Tidal range you have shown in the previous slide actually. 1 meter.
1 meter and 1.8 meter, yeah.
That much influence how it is coming actually, like salinity intrusion. Your salinity intrusion you are showing, no?
Yeah.
That much influence how it is going to the top. Very low height actually.
Up to, for Brisbane River is up to 5 kilometer.
Height is low, how it is that much length it is moving actually, I must say.
Yeah. Yes. Yeah. So you have the similar tidal range here.
Similar type.
Same.
That much intrusion is not going. Tidal range 1.3 Chennai.
Very limited. So what's the tidal? Also, that depends on the topography. So if you are very flat, then the tidal range will be much longer, right? So if you have a certain slope, then the tidal range will be smaller.
That's why most of the design will not consider salinity in the riverine discharge. Only will consider riverine discharge only in the design. Salinity is not a major part here actually.
Here?
In our designs actually, imposed. In our designs, if we are including the riverine also, we will not take salinity as a part actually.
So you mean in your design, you don't consider the salinity?
In the river discharge is enough.
Okay, maybe your river discharge is much higher. Is that right? Yeah, yeah.
Here you are showing that so water quality parameters also affect.
Your river size, the discharge rate is much stronger. Ours actually is not big, our river, because Australia is relatively flat. So we don't have a big reservoir or big mountain yet. So our river flow is relatively small. Yeah. So the intrusion is very strong.
And you are having that much riverine discharge data you are taking continuously monitoring. Then that flood estimation you are not done in 2011. You are said like it is flooded.
We have what we.
Here you are shown from area 2011 it was flooded actually.
2011 we got the flooding.
Actually.
Yeah.
You are having riverian discharge, actually you could not able to, amount of flood you could not able to estimate.
Yeah, for the sedimentation, yes. So that's what I mentioned, that we use a satellite image and correlate with the previous concentration information. Then we derived a data-driven model. So we based on the discharge rate and correlate the concentration information and use that into the model and then drive the model. Is that your question? You said I don't have the measurements during the flooding period.
Flood time, but you are monitoring, what are the things you are monitoring every system? Water level also?
Yes, water level we have. Water level is just the gauge station is always there. Yeah, the gauge station is there. But for the sedimentation, we don't have. Yeah.
In your location, what is the tidal range? In your location, Brisbane location, what is the tidal range?
1 meter for the nip tide and 1.8 for the spring tide.
Same like here also, same.
It's the same,
Same.
similar. Yeah, I think
But-
our latitude is about 28. The latitude. Yours,
But your beaches are flat. Our beaches are too steep. East coast, our beaches, too steep beaches. In your area are flat beaches.
okay. Yeah.
But here, flooding is more.
You have more.
Discharge is more. Flooding is discharge is more. So that we didn't consider salinity here.
You consider salinity.
We
You
consider,
didn't.
consider salinity.
So you don't worry about the
Salinity.
salt water intrusion.
Yes. Discharge is more now.
But what about the aquifer? The groundwater? No.
Discharge is more. Flooding is more. Salinity intrusion is not bothered.
But do you have any like a simulation or monitoring how far the salinity has been intruded?